Okay, so today we begin respiratory mechanics, and this will take at least both of the hours this morning because this is a pretty big subject. Okay, well, so the underlying principle that you need to know intuitively is that air goes from high pressure to low pressure. Okay, so here we have our simplified respiratory system. We have the conductive zone of the airways shown as a tube, and then we've combined all the 300 million alveoli into one big alveolus at the bottom. So we're looking at pressures, and the pressure in the alveoli is alveolar pressure, that's uppercase A, as opposed to lowercase, which would be arterial. Okay, and then we have barometric pressure outside. Okay, well, so because of rule number 1, if alveolar pressure is greater than barometric pressure, air will flow out of the lungs. If barometric pressure is greater than alveolar pressure, air will flow into the lungs. Okay, so what we need to do in order to move air into the lungs is to create a pressure gradient. Okay, and so we need to somehow change either alveolar pressure or barometric pressure. And there's a Buddhist proverb that says it's easier to wear sandals than to pave the earth with leather. Okay, and so this applies in this situation. It's easier to change your alveolar pressure than to change atmospheric pressure in the entire earth. Okay, so we have to figure out a way to change alveolar pressure, and how are we going to do that? Well, we can use Boyle's gas law. Okay, and here I'm in Oxford paying homage to Robert Boyle. This is where he invented his gas laws. Okay, and Boyle's gas law is fairly simple. It just says pressure times volume divided by temperature is constant. Okay, and so he's talking about the pressure and volume in an enclosed container. Okay, so here's our enclosed container. There's gas inside this container at a certain pressure and a certain volume. Okay. Now, if we do something to change the volume of the container, and this is a closed container, so the same amount of gas is still in it, okay, we've increased the volume, what's going to happen to the pressure? Decrease, right. Because pressure times volume is constant, so if we increase the volume, we have to decrease the pressure. Okay, so if we want to decrease the pressure in our lungs to get air to flow into them, we need to increase the volume of the thoracic cavity. Okay, so this is a cross-section of a human being, and it shows that things are unfortunately a little bit more complicated than kind of the balloon that we drew. Okay, so we have the lungs surrounding the heart, okay, and the lungs are entirely enclosed in a pleural membrane called the visceral pleura, okay, visceral pleura. Okay, this goes all the way around the lungs. Okay, and there's a second pleural membrane that lines the inside of the thoracic cavity. This is called the parietal pleura, and parietal means like to the side or on the wall. So this lines the chest wall. Okay, so these two pleural membranes are very close together, and there's a small space between them that's filled with liquid called pleural fluid. Okay. And when you expand the thoracic cavity, the pleural membranes move, but they move together, okay? And they move together because there's very little space between them, and the space is filled with liquid. And so if you think about, if you have two pieces of glass with water between them and you try to pull them straight apart, you can't do it because pulling them apart decreases the pressure between them. You can slide them, but you can't pull them straight apart, or a suction cup on a mirror. If you try to pull it off, it pulls back because you decrease the pressure between the suction cup and the glass. Okay, and so this is the same thing. So the pleural membranes tend to move together, but they are two distinct membranes, and they can slide over each other. Okay. All right, so this is a cartoon view of this. So we have our chest wall. Okay, it's totally lined by this green parietal pleura. Okay, and then the lung inside surrounded by the visceral pleura. Okay, and this pleural space here is larger than it would actually be, but it's just so there's a, it's just a cartoon. Okay, so this is kind of almost a virtual space. It's filled with pleural fluid. Okay, but the reason we need to talk about it is that we want to think about the transmural pressure. That's the pressure across the wall of the lung. And the transmural pressure is the pressure inside minus outside. And so the pressure outside the lung is the pleural pressure. Okay, so that's the pressure that will, that's relevant to lung inflation. Okay, so transmural pressure is always the pressure inside minus the pressure outside. And so in this case, the transmural pressure is the alveolar pressure, pressure in the lung, minus the pleural pressure, which is outside. Okay. See. Okay, so one final thing about the pleural pressure. Okay, the lung has elastic recoil, and it's always pulling inward away from the chest wall. And as a result, the pleural pressure is always more negative than the alveolar pressure. Okay, so the chest wall is there, the lungs are contracting, their elastic recoil is pulling them away, and so the pressure, the pleural pressure is always lower than alveolar pressure. Okay, so if we look at the system at FRC, we have 2.5 liters of air roughly in the lungs. Okay, we're at FRC, the system is relaxed, this is the resting volume. Barometric pressure is 0, alveolar pressure is 0, there's no airflow. We're ready to inspire if we want to. Okay, now it turns out that the chest wall would rather be at a larger volume. Okay, and so if we took the lungs out of the chest wall and looked at them separately, the chest wall would expand up to 4.5 liters. Okay, and the lungs would contract down to 800 milliliters. Okay, and 800 milliliters is called the minimal volume of the lungs, and this is lower than the residual volume, so this is less than lungs can ever achieve inside an intact human being. Okay, so due to the elastic recoil of the lungs and the chest wall tends to be pulling outward, the lungs are pulling inward. So at FRC, the chest wall is pulling out, the lungs are pulling in. Pleural pressure is negative, okay? And so there's this kind of tension between the lungs and the chest wall, and the pleural pressure is going to be negative. So here we're saying it's -5. Okay. Okay, so there is one situation where the pleural pressure might not be negative, and this happens if you were, say, stabbed and the knife punctured your pleural membrane so that air could get into the pleural space. Okay, air in the pleural space is called pneumothorax. Pneumo is air or breath, and thorax is your chest. So, and actually the Greeks thought pneuma, air, that air was sort of contained your soul. When you expire, when you die, you have your last breath and your soul comes out of your body. Anyway, so pneumothorax, you puncture the chest wall, air can get into the pleural space, and under these conditions, the chest wall will expand out, the lungs will contract down towards their minimal volume, And you can't breathe because breathing requires the pleural membranes to move together. Okay. If you go hunting deer with a bow and arrow, you shoot Bambi and the arrow punctures the lungs. Bambi will die of pneumothorax. And this is because air gets into the pleural space. Now, it turns out that in elephants, the pleural membranes are physically connected together. And so if you try to shoot an elephant with a bow and arrow, probably the arrow will bounce off the skin. But if you do manage to pierce the lungs, you wouldn't kill the elephant because the pleural membranes stay together, so he could still breathe, but he would probably stomp you into jelly. So you've learned something useful today. Okay. So that's our system, and let's look at what happens when we breathe. Okay, we start at FRC. We contract our inspiratory muscles, the external intercostals and the diaphragm. Okay, this decreases pleural pressure, which increases alveolar volume. Okay, and this is Boyle's gas law. And we've increased the volume, which decreases alveolar pressure. Okay, and so as a result, alveolar pressure is less than barometric pressure, so air goes in. Okay, so air comes into the lungs. We're contracting our inspiratory muscles. We've expanded the thoracic cavity. Air comes in until the alveolar pressure equals barometric pressure, and then airflow stops. Okay, so that would be the end of inspiration. Okay, and normal expiration, we start from our and inspiratory position, and we just relax our inspiratory muscles. Okay, this increases pleural pressure, decreases alveolar volume, and we've decreased the volume, and so this will increase the pressure, Boyle's gas law. Okay, and so now alveolar pressure is greater than barometric pressure, and air goes out.